Sure.
Everyone, please mute
Yeah.
like
Hey,
if
good
you're
morning,
not
guys.
talking. Thank you.
Sure, thanks. Hey, good morning, guys. I don't know if all of us are in the same time zone, but yeah, good morning, good afternoon, based on wherever you are. Thanks for taking out time to join the session early morning. Yeah, I'm glad that you all showed up here. Let's just try to talk about whatever we can in this 1 hour and discuss. I mean, it's an interactive. I'm trying to keep the session interactive, not on just the not as a just one-sided conversation. We just try to make it as interactive as possible. And I'm not gonna talk about log theory here. We'll just try to do some hands-on and see what we can take out today with us from the session. So as my friend Nafos here gave you the introduction about CGC, what we do as an organization, the sessions we conduct and all, please try to utilize this opportunity that we are offering free of cost. We do not charge anything for it. It's really good for professionals to network and for freshers or the students to know what's going on in the industry and get connected to professionals who are working. So yeah, please utilize that opportunity if you can. So let me go directly to our topic today. I'm trying to cover here Scala, Akka, and Kafka, and we're gonna see what each of them are and what they do. Okay. So here, Scala is a general purpose programming language which does offer object-oriented functional programming paradigms to us. So before starting, I just want to see what kind of audience we have. Can you guys quickly raise your hand and tell me who has some programming background? That just gives me an understanding of what kind of audience we have and we can drive the session accordingly. That would be a great favor if you can guys do it. Can you just raise your hand here quickly? Yeah, only the guys who have programming experience of any kind, please do raise your hand. Like maybe anything you learn in school or you work wherever you are. Okay, thanks. That at least give me a sense that 50% of the participants are aware of our programming, but I guess we can start our conversation. So, okay, let's start with it. Sure. So here, Scala is a typical programming language. Like, I mean, you can just see it as any other programming language that we have out there, maybe C, Java, or anything. But it offers us, it's different in a lot of ways, and we'll talk and see how it is. So Scala is, as I said, Scala supports both object-oriented and functional programming. Yep. As a lot of us are aware, of Java and the programming languages .NET, we'll see how those concepts correlate with Scala and why we're moving towards Scala. We'll talk about it. So here, Scala follows a top-down approach, wherein it, let's say if you write the program, it breaks down each of those components into smaller parts, like smaller components, and it tries to execute it in parallel. I mean, it won't be executing that sequentially, thus giving you the concurrent, thus following the concurrent approach and making the program more efficient in terms of time and resources. And that's what top-down approach is for doing it. And it provides the Scala library of Scala programming language provide seamless interoperability with Java, as in you can write your code and basically in Scala and still make use of all the libraries, jars you have available in Java as well. Like let's say, for example, you're trying to connect to a driver, a database, you can still use a JDBC driver written in Java to connect to, written in Java, still using Scala. So any of the libraries that are available to Java are seamlessly interoperable with Scala ecosystem, as Scala is still getting compiled to a bytecode which would be able to run on any JVM. Like wherever you see Java running, Scala can also work there. Please feel free to raise your hand, or someone can interrupt me if you see my voice is not clear, because we have lots of connectivity issues with this. Please feel free to stop me there if you have any issues. Yeah, so some of the major features, or some of the very wonderful features that are offered by Scala are type inference, lazy evaluation, immutable variables, high order functions, nested functions, case classes, pattern matching, and options. I mean, we'll see each of these. Some of these, we cannot cover each of these. We'll see some of these features today on our exercises, and we'll talk about it in a second. So here, when I say type inference, in Java, let's say anything you write, right? Let's say you're declaring a string. You'll say public string, for example, str, right? Equals to, you assign it whatever value you want. That means your str is a variable name and string is the data type that's going to return. You'll have to type explicitly there. But with Scala just gives us three ways of defining variables: val, val, var, and def. That's how we can define our variables, our functions, everything. And we'll quickly do a run on it. Give me a second. Okay. I hope you guys see my screen. We'll just see what we are doing here. So, and higher order functions is a concept wherein we have seen in Java or any other programming language where we can pass in any values to functions, right? Basically, a function is a parameterized, or you call it method sometimes. The method takes parameters and it does some computations, it does some processing, and just gives you some kind of return value. But that's what we have seen methods do. But in Scala, we have methods, we have functions, which takes in another function as a parameter and just gives you a value. We'll see that's really interesting concept, and we'll look into it in a few minutes. And the case class is another fantastic example where we can where we see how Scala achieves what other programming languages offer with very less code. Like, I mean, probably you can write 10, 12 lines of code in just a single line, and we'll see how does that work. And pattern matching is another concept where we have pattern matching in many languages, where we can have the pattern matching on primitives, like especially the case match statements. But here we'll see Scala has a very strong pattern matching, wherein we can do pattern matching on strings, on classes, on various other types. It's really strong in a sense. It has a lot of ways that you can do your pattern matching, and we'll see some examples of it as well. So let me just quickly walk through the hello world example. Like, I mean, you see the sample. I try to write a sample hello world program here, which does create a class where objects are singleton in Scala. That means only one instance of that object can exist anywhere in the application. So basically, I have a hello world object created in Scala, which is extending something called app. You can ignore it for now, but just assume that all the functionality of main method and all that boilerplate code is hidden or abstracted in the sense in the app trait. Like, we have a concept called trait, just like interfaces in Java, but I mean more enhanced, I would say. The functionality of interfaces and abstract classes is combined together with the rich semantics in an efficient way in a trait. You can, I mean, I can provide you all the documentation where you can just go and read about it. And I mean, we can talk offline as well if you have any questions, or we probably can help you. You can send me an email on it. We'll see here. The only thing that I'm doing is just saying print hello world. Like, I mean, we'll see. I'm not gonna create an object here, but we'll see how that print statement would work. So this Scala provides a REPL. That's what we called REPL, REPL. And here we'll see how we are able to print it. Let's say I'm just writing hello world. So that's what all I need to do. And there are no semicolons. There's nothing else. Just say println and just have your string printed out. That is a simple syntax or a simple statement that I have here. Let's go to our next slide and see some more examples of Scala that we're going to see today. Okay. So here, let's see what, as we just spoke, let's see what higher order function is and how does that work. I'm creating a list. most of you might be aware of what list does. Just like any collection in any other programming language, lists are collections in Scala as well. I'm just trying to create a list of integers, let's say with 5 numbers, 1, 2, 3, 4, 5, and I have a list created. If you see on the next line, the moment I entered, the moment I hit enter, I see this getting compiled here, right? This auto-generated by the compiler. This called type inference. I did not give what type of variable it is, what its return type is, what kind of values it's going to have, nothing, right? So, and Scala just literally told me that it is a list of integers, right? And another way of writing it would be where I'm explicitly specifying what type of variable it is. You see here, and this is exactly the same. Like if you see this line, there's no difference between here and here, just a different way of writing it. But we still prefer writing this way, specifying the types explicitly, just to make sure that your return value from the expression on the right hand side is exactly return the same thing as expecting on the left hand side, and it avoids the runtime issues because the compiler detects it on runtime. We just try to compute it on the compile time and try to find out what kind of values we have on the expression coming out from the expression. That was just one of the example that I just gave. Let's have the list there, and now I'm trying to do. Let's see, I'm trying to have a function that just calculates factorial. I think factorial is one of the basic functions or methods that most of us are aware of. We just copy this code quickly from here and try to see how would that work when we use that in the REPL. Okay. There's something called paste mode in the Scala REPL here, and you can just paste all your code and just hit Control D, and your function is compiled. You see here we have a function now which is taking an integer as a parameter, and it has a return value of int. Okay, so let's see. And the way I wrote this function, if you guys can look at it, it's a recursive function, and we call it as tail recursive. That's one of the functionalities of Scala. Functions in Scala are always preferred to work with immutable variables like immutable data. It should be a function should preferably be always a pure function, as in it should just work on the set of values, set of parameters it takes, and there shouldn't be any side effects. Like I'll give you the input and you just give me the output. You don't modify any state ever, unless that's specifically the need. But the priority is always to keep a function pure without any side effects. As you see in the case, we're just providing a input parameter called x, which is an integer, to factorial, and we have another function. This is the nested functions because we have function within a function here, and we have another function called fact, which is taking an integer and another integer called accumulator, right? And it checks in if the value of the input passed in, that x, is less than or equals to 1. We are just returning the value from the accumulator. And you see below where I'm calling in fact, I'm saying call a function fact and pass in the value of x, which is passed in to factorial, and then one value to start with. We will see what will be the result and output of it. Okay, let me quickly type out. So let's say I'm creating another variable called numList factorial, which does iterations, which performs map function, which runs map functions on a collection. Here, when I do .map, map is a function that is available on a list, which is a collection here in Scala. And now we are passing a function factorial to another function map. Like I hope you guys understand this concept here. Like this is what higher order functions does. Let's see. So now if you see, map in itself is a function which is accepting another function as a parameter, which is factorial here. And now there is another way to write it. You see, if the output of our num factorial list here is list of integers with the factorial values of these numbers, like 1, 2, 6, 24, and 120. 5 factorial is 120. So let's just see how we can write it. If not this way, then let's say Map just gives us, it does operations on each of the elements at once. So here I'm saying x is, let's say, factorial of x. I'll be passing it. This is another way I can call in just syntactic sugar that I was just passing in the function, because the function will always take, in our case, only one value. You see, still the output is same. I mean, there are many ways to write this. It just depends on how comfortable you are in coding it out. So I'll just say, for example, underscore, right, factorial of, I'll just say underscore again. So you see now the result that we got is different. Instead, we got functions, we got for everything, because Scala here doesn't understand what does underscore mean in this case. And we'll see how we can sort it out. Does it make sense so far? I mean, let's unmute ourselves. I mean, I just want it to be interactive. So it helps me if you guys can talk. Can you unmute yourself and acknowledge if you guys have any questions or anything you see here missing?
Any workbench for Scala, like rather than working it in a command prompt, like ID?
Yeah, we do.
Thing? Okay.
We do. We will look at it in a minute. We can use any IDE for writing Scala code as well, just like for Java, we have Eclipse, we have IntelliJ. We can use any popular IDE that works with JVM. I mean, that should just be fine. We should be able to use it. Let me move on to the other concept that we have called options. If you see here, I'll come back to case class in a bit. Here, if you see, I'm going to create an option. Options are one of the very beautiful advantages that we have, and that overcomes the null pointer exception scenario. So typically, when we work with other libraries, I mean other languages, and especially when we do I/O operations, when we read data from any database or any external system, in the sense, there might be chances that we might get a return value as null, and then you try to access that value, and there'll have to be a lot of boilerplate code that we just have to have just to handle that null. And here we'll see what does Scala offer us. There's something called option, wherein we can just say, let's say some value here. That's how we just have in the syntax. So if you see the return, the output for it is an option, which is an option of string. That now means sum, right? So what does that mean is option will give us the ability to handle null. Like when the value is empty, it just takes it as none. We'll just see how does that work. You see here, now it says none. I mean, it doesn't fail either. So let me explain you how does this concept work. And now if you see in both the statements, the line I have here, which says option of string, it's just type in front that's just triggered in, and it tells us what exactly it is. Option is of type option of string, whose value is sum of test. And in the other case, we have the same variable and just the value was none, and now we have none dot type as the type of the option here. And we'll see that's exactly why I was telling you it's not always recommendable to let it on the compiler to handle the type inference, and we'll always recommend to have it custom. Like we want the developers to take care of it. So here I'm telling this variable should be of type. It should be of type option of string. Always wanted this is a option of string. I mean that means it either exists. If it exists, it should be a string. If it doesn't, then it doesn't. It's none. That's what the option means. So I'm creating an option whose value is none, and let's see what is the return type. You see the difference between these two statements here. Here we have the same code that just same value assigned, but the type inference was different. And here with just explicitly specifying the type of return values expecting, the scenario is different here. So that just gives us an advantage in handling and reduce lots of our boilerplate code that we might need to write in handling the null point exceptions. Let's just quickly move over. We I think are already 25 minutes ahead. So here we'll see case classes, right? There is a lot of code that we need to write again in Java. If you see on the right side here, right side of my screen, I just divided it in two parts. You see, I have an example Pojo class. Let's say you're creating a product class, and let's say you're trying to do a database mapping from here, and just trying to read out the data from a database or writing to it, or whatever you do. So you have two variables defined, ID and category, and just trying to have the getters and setters to work with, right? You see, probably you have around 15 lines of code, and on the left side, you see the case class section. I just have a single line called case class, and we'll see how does that work quickly. So I'm just saying case class product just takes just has var int ID, which is an int, and then I'm saying var category, which is an int as well. Sorry, which is a string. Okay. So here you see we defined a class called product. And now we'll see how does the getters and setters work, and how if I have to access the value, how do I instantiate it, how do I access the values, and basically get and set values in it. So I'll just take a variable called p and just say product here. We'll just pass in the parameters. Let's say product number 1, and I'm just calling it as fruit, for example. Okay. And now we have a product called p, and the value that we assign to it as ID is 1 and the category is fruits. Now let's just see how the getters would work here. I'm just saying p dot. You typically do get, like basically you call the get function, like you say get ID, but in here we just don't need to say anything, just to p dot ID. We'll just take care of it. We'll just give you the value of ID from your instance, from a p instance. And now I'm going p dot category, which just gives you fruits. And now let's say what if I have to set the value here, maybe something else. Now when you see it got overwritten, right? So that's the beauty of Scala. I would say it's really awesome to see the same thing getting accomplished with less lines of code and with much simplicity. So let's move on. Let me know if you guys have any questions in Scala. We're just trying to switch over now to Akka, which is a framework, and we'll talk about it, what it does. I just try to keep it simple, just to give you guys an introduction and a flavor of what does Scala do and what capabilities on a high level it has. You can unmute yourself and ask questions in between as well. I mean, we anyways have a Q&A session at the end, but still, if you guys have any questions, you might forget until the end. Just feel free to ask if you have any. So here we are talking about Akka, which is an open source library for building highly concurrent, distributed, and fault tolerant applications on JVM. I mean, an Akka is built with Scala. Basically, all the Akka library is written with Scala. As we have just seen in the Scala examples, how the code works concurrently and basically in parallel. That's the beauty, that's the approach that Scala offers us. And we'll see how does Akka works as a complement to Scala, and they both are enabling us to create highly scalable distributed applications. So an Akka works with the concept of something called actors, which are central to the concept of Akka, and they work together, they communicate together. Basically, they work as a cluster and communicate with each other in accomplishing our task. And we'll see how it is. And I have some examples for it as well. We'll see. And now Akka works as a cluster. When I say a cluster is a group of nodes that just talks together through some kind of mechanism, like either through direct messaging, message passing, or through distributed messaging using some distributed message queue, just like Kafka or something else. And here actors provide us it provides us location transparency, as in, let's say we have three actors in our actor system. Let's say we have three nodes basically, and three actors, one actor in each of these nodes. Now actor one doesn't really need to know where does the actor two is in the system to talk to it. Like, I mean, we will see how that's really beautiful to see, how you can just say, hey, call actor two, I just want to talk to it. The actor system will find actor two for you, and you can just send a message to actor two, and that's how the actors communicate asynchronously in one blocking fashion. And actors follow the let it crash philosophy, in the sense, if something happens to an actor, like let's say there is an exception which is not handled, or if there is any unforeseen scenario we just we just cause the actor to crash, to die. And basically we have a supervision strategy here for each actor. The actors are created in a hierarchy, like, as in each actor has a supervisor which will be looking over it, managing the life cycle of that actor. If something goes bad in that child actor, the supervisor has the capability to watch over it and decide what to do with that failure. And we'll see how it's done here. And this library provides us a unified way to build scalable and fault tolerant system. Scalable in the sense you can spin up like hundreds and thousands of actors on just one node, and each actor can have multiple instances running, and they just work together and get the job done. This has the ability to scale up on multi-core system. Like, it uses all the functionalities of the multi-core processors today, because based on the number of threads and based on the number of codes, we can configure and tweak how many actors we want for scaling up. Like, let's say initially to just get started, you just have 4 actors, and now if you have more cores in your machine, you can spin up as many number of actors as you want based on your capability. And you also have the option to scale out, in the sense, if you see the traffic to your application is increasing, and when there is a huge demand, let's say, for example, as all of us are aware, like typically the example of, I would say, some university website, right? When there is a results announcement, we'll see all the servers not performing well, not coping up with the demand, in the sense, like, it just takes in forever to just get the result from there, right? In those kind of scenarios, when you know that there is a particular time when the demand is going to be huge, you can just spin up few more instances of the application, and it just takes care of it. You don't need to do anything else. And definitely all of this is in cloud. Like, you can write the applications on premise, like on your hardware, or you can also write this in cloud. You can just spin up an EC2 instance and just start your application there. And the other wonderful advantage of using Akka is, if you guys remember the way we code in Java, if you want to have let's say any blocking calls or any sensitive calls that might just take too long to execute, there will be having the issues of thread locking, thread blocking, deadlocks, and all that stuff which we need to take care manually. And here, writing concurrent systems is much easier, in the sense all that thread handling, thread management will be taken care by the Akka library itself, and just gives you a higher level alternative, which is much easier to work with, and just keeps the low level mechanism just abstracted with you, and you don't have to get into the details of it. I mean, definitely you understand how it works, but you just don't have to have the boilerplate code to handle that part. Here is the supervision strategy I was talking about. This is how Akka works. Let's say whenever so the way main method is an entry point into a Java program, we have an actor system as an entry point into Akka. If you see on the last bullet point that it says an actor system is the initial entry point into Akka, that's how I create the actor system. Like val system. Val here says we use for immutable variables. Scala and Akka, these languages or frameworks prefer immutability over mutability, because we prefer to work with immutable states unless there is a specific need where you want the variable to be immutable. You always it's recommended to go with the immutable variables, because you would know you can expect what the variable will be or where would that change. So there won't be any unexpected state changes. That's the reason we always prefer immutable. We will see how do we declare or define vars. I mean, there is I forgot to talk about it. Let me just quickly cover on, let's say val a equals to 10. We'll switch back to Akka in a second. Let's say I'm just saying val a equals to 10. And now I just state val a, which is an integer. If you see the next line here, now a is of type int. If I'm trying to assign some of the value to it, let's say now I'll say ABC, it won't work because it says reassignment to a val. So your val is immutable now. If you want it to be mutable, then you'll just go ahead and just say var is ABC, and now you can define it the value of 10. It will still work. Wow. Give me a second, something wrong. Oh, I mean, I cannot change the type for sure. Yeah, definitely. I cannot change the type, but it's still mutable. You can change the value to it. Let's say I'll just call it DEF, for example. You see, because once you create the variable, its type has changed, and unless you redefine it, I mean, definitely you cannot reuse it. Sorry, my bad. So I just wanted to show you how the val and var works in Scala. There is something called def as well. We'll talk about it. I mean, it's for the context that we're talking about, it's not necessary for now. We can just move on and come back to it if needed. So here we have seen the actor system is the entry point to an actor. So whenever we say val system is actor system, we create an actor system with just, if you see on the top here in the diagram, I'm saying root guardian, user guardian, and system guardian. These are the three actors that get created by default in the actor system, which manage the whole show. Now we are talking about creating an actor. Like, its actors are logical grouping of the concept. Like, let's say you have an actor for handling your transactions. For example, let's say an e-commerce website, right? You have an actor just does take care of the order processing. That actor does just takes the orders and handles all the other processes related to that order. And we have another actor for handling the payment. So it's just a logical grouping, I would say, or the logical. But basically, it's event driven and domain driven as well. Basically, it gives you the ability to group the actors together and name it something. So here, whenever we create an actor, it just gets created under the user guardian. If you see here, the red line that says system.actorOf, that's how we create an actor. If you create an actor called some actor, then its relative path will be /user/some actor. That means it always gets created in the user context. Now, anything that happens in the some actor, if you see the next line, I'm doing user, some actor, and some child. Now, anything that happens in the child, my some actor will have the complete control of what to do with it. And we'll see what all supervision strategies we have on the left. I'm talking about the supervisor here. The supervisor delegates tasks to subordinates and therefore must respond to their failures. And we'll see the supervisor takes one of the following actions in case of failures. As we just spoke, if something happens in child, if there's an exception, unhandled exception, there's some unknown issue, then we have these four options. Like, we can ignore that exception or error and resume the functionality as usual. Or we can restart the whole functionality. Let's say we can just restart the whole actor and let it start from beginning. Or we can just stop that actor entirely and let it collapse. Or then we can escalate the function. Like, I mean, the whole system would crash. You can just keep escalating it. If you let's say now, if your application is dependent on a database, right? If that database doesn't start, you don't want your application to start, for example. In those scenarios, if your actor fails to connect to the database, it will crash, saying some exception, connection exception. And now, if your supervisor knows that if in case of connection exception, just let the whole system crash. It will just escalate that exception upwards, and eventually it leads to the whole system just crashing down, and then you can handle it accordingly. And here is a sample code, and I try to put in together what kind of companies are using in Akka today. If you see all these companies, Walmart, Capital One, PayPal, Amazon, I mean, Starbucks, iHeartMedia. There are lots of companies. I mean, I cannot. Yeah, please.
I have a question. Like, is this Akka framework is it applicable for only Java-based applications or any kind of applications independent of the
Yeah,
core
it
language?
has no. The Akka library. Akka has APIs for both the Java and Scala, but they
Mhm.
also have a module for .NET as well. Like there is something called Akka.NET for .NET folks.
Okay.
Even
And
for
like,
exploring it.
can
Yeah.
we implement this framework for the projects which are already in implementation and already in live state?
Yeah, definitely. I mean, I didn't get the question exactly. What do you mean by
Let's say
existing
my
application?
project is completed around 5 years ago. Now I believe that it is going. I'm scaling it too much more higher. Right. So, like, can I integrate this framework in between?
Your voice is breaking. I cannot hear. Can you please repeat that?
Okay. Am I clear now?
Yes, yes, it is.
Yeah. My question is, my project is already completed. Like, after 1 or 2 years, I want to implement this framework into my project. So,
Mhm.
will it support or
Definitely.
again? Yeah.
No, definitely. But you will have to rewrite it, right? I mean, because once you're saying your project is complete, then we are talking about complete different. I mean, it's basically a moving. I'm saying it's just a complete shift of the technology, right? You'll have to rewrite it. I mean, definitely it would work
Okay.
as
So I
well.
have to rewrite it.
I mean,
Okay.
unless yeah, definitely.
No, I cannot
Because
integrate it.
syntactically and semantically. No, it's not
Okay.
integration, right? Because if there's only
Right.
one part, then probably yeah, you can expose some REST APIs to handle it. But yeah, I think you'll have to rewrite it.
Okay. Got it. Thank you.
So here we'll see quickly sample code that we have for Akka. We'll see how an actor is created, how the actor system is created. You can see on the top, I'm just creating an actor. So every actor by default extends uh, an actor trait, and here we have a receive method. So as I just spoke, right, actors only talk to each other by message passing. Like traditionally, if you see in the Java world or any other programming language, right, we'll have classes exposing the methods, and we will know what all methods are available to us to use to talk to the class, right? But here in this case, we do not know actors doesn't expose us anything. We can only see what they can do by just passing a message, and they only every actor handles certain types of messages here. So if you see this actor that I have here, that called print my actor reference actor, that just has a receive method, and in the receive method, if you see the case says print it, and now I'm gonna only handle the messages of type print it. Anything else, I just don't understand. I just ignore it. You can just say it as a robot not understanding anything else. For example, we say hey Siri or hey Google, okay Google, right? Then only they'll respond. Anything else, they just don't get it. It's out of their scope. And in the case print, I'm just saying val second ref is I'm just saying hey create another actor called second actor, and in the second line in the print statement here I'm saying print out the whole reference, like basically the whole path of that second ref that you just created. And let's get down here and see what does this object do. We have created an object called actor hierarchy experiments, which is extending an app. As I told you, just ignore what does the app is. Just assume that it just gives you the functionality of and the boilerplate code that you have to write, handle the main method and all. So just ignore it for now. And here we are saying creating an actor system, as we just saw earlier in the earlier slide, how to create the actor system here. We created an actor system, and on top of it, we have created an actor in the actor system using the syntax system.actor_of, and I'm passing which actor I want to create an instance to. And here I'm giving it a name called first actor. And in the next line, I'm doing print statement where I'm saying print out the reference of first ref which you just created. And I'm just doing a tell call. You see here, I'm saying first ref exclamation mark and then print it, right? Print it is a string. And now we are basically, that's what we call a tell call. Exclamation is tell. Like basically you have three ways to talk to actor. That is tell, ask, and then forward. Tell has a syntax, tell has a symbolic expression of exclamation, and then ask has a symbolic expression of question mark, and forward is just a method call. And here, when the moment we say first ref tell printed, now this message will go to the actor mailbox to the actor. And now if the actor is handling the message type printed, then only that actor will understand what does print it mean. And it will go ahead, and if you see the output here on from the main method, the first thing that gets printed is the first column, the reference, the complete path to the first actor. And on the second line, we see the second getting printed, where we're printing out the whole reference or the complete path of the second actor, which we created in our print method, like basically in our print case. Yeah, let me know. You guys might not get everything on the first introduction or just now in the conversation. I'll share some resources with you. You can just go ahead and try. Just explore what this technology is and see how you guys like it. And we'll talk about the opportunity that we have in this domain, in this technology in a bit. I'll just go pretty fast. We only have 15 minutes. We'll have to cover a lot more. So here is we're gonna start talking about Kafka now. Kafka is a very popular distributed message queue that's being used now. It's being used in the big data domain. It's being used in application development. It is being used in IoT. Lots of other things as well. Anywhere you see, basically, I see Kafka everywhere these days for most of the functionalities that we see, and most of the Fortune 500 companies are using Kafka now. So let's see what Kafka is. So Kafka is all built for distributed messaging, and we see what distributed message is. It's based on the concept of reliable message queuing. That means, let's say you have a queue to which you are writing messages, and that just messages needs to be handled all across the board. When you say distributed applications, they can be on different machines, they can be on different regions. Basically, when I say regions, it can be countries, it can be continents, it can be anything. So now, for all these applications, for all these nodes that are spread across the regions, there should be some way to talk to each other for instructions or for communications or for anything. So that's where the Kafka fits in. It's a perfect fit, actually. Kafka was created by LinkedIn in 2011, and that's when they open sourced it, and it has grown a lot since then. Kafka combines three capabilities as a core. It just gives us the ability to write and read messages from the queue, and then we can store those events durably and reliably for as long as we want. Like, we can tell the Kafka how long to persist those messages for: 12 hours, 24 hours, 7 days, 24 days, 30 days. It depends on the message size. It depends on the size of memory you have on your nodes, and you can handle it accordingly. And here we also have the ability to process these events that we are sending to Kafka in real time or whenever we want, on demand. Here, the moment you write messages to Kafka, it just doesn't go away. Let's say you have we'll talk about it in a second. Let me just cover this first. So Kafka is a distributed system consisting of servers and clients. Server takes care of the data storage. Server takes care of all that management on distribution of data and handling of the communication between brokers and all. And the clients communicate with each other using high-performance TCP network protocols. Kafka works as a cluster of one or more servers that just span across multiple data centers, I just spoke, or cloud regions. Like, Kafka can be on one machine, like one box, or multiple boxes, and works as a cluster, or it can be spanning across multiple regions or multiple data centers as well. Like, we typically have data centers on region based. Let's say we have one data center in Chennai, for example, in India, and the other one is in Mumbai to handle the traffic geographically. And we'll see how those things work and what the advantages going forward. So here, clients allow us to write distributed applications or microservices that read, write, and process streams of data in parallel at scale. You can write hundreds and thousands of messages to Kafka and read from it in real time without any lag. And as it's fault tolerant, even in terms of crisis, in terms of failure, we have a way to read it back. And one of the beauties of this mechanism is once once the customer once the customer once the consumer reads the data, it just doesn't expire. It will still be there in the queue. And when in terms of failures in the client has the option to handle the failure accordingly. Either it can restart, either uh, it can ignore it and handle it. We'll see how does that work. So here is the anatomy. Like Kafka has topics. In the sense, topic is a logical grouping of messages, I would say. Let's say you have, as I just gave you the example of actor for handling the ordering flow, right? In an e-commerce website, just you can say all the events or all the records related to ordering. You want to put that all in a topic called ordering, for example, and that topic will have number of partitions. You have the control of defining how many partitions you want on a topic, and that is always an architectural decision which you have to decide how many number of consumers you have, and then you can basically consumer groups you have, and then you can create the partitions accordingly. But I mean, for just to keep it simple, the what Kafka recommends is to have 3 partitions and let it handle. Here we see an event records that something happened. As we started with an example of e-commerce website, let's say an order just got processed, or Swiggy or Zomato, right? For example, we're just giving a lot of orders for food. Let's say you ordered an ice cream, and that's an event, right? Basically, ordering of that ice cream from your home is an event for Swiggy. It just puts that in a Kafka topic, like something that really happened, which has an event key. Like basically, let's say I, Naseer, what did I do? I ordered an ice cream from, let's say, for example, some ice cream store, ABC. And when did that actually happen? We have an event timestamp for it. The key concepts here that we see in Kafka are producers, consumers, topics, partitions, offsets, and we see what each of those are here. So you see on the right side on the diagram, where I have the diagram for anatomy of a topic. We see a list of partitions 0, 1, 2. And I just said Kafka recommends 3 partitions by default, and it's always tweakable. You can configure it. And you see it's always written on the end. I mean, if you see the arrows pointing there where you see writes, and the offset starts from 0. You see 0, 1, 2, 3. That's the offset. That is a unique number assigned to each event or message to Kafka topic in each partition. Each partition has its own sequencing, own unique IDs assigned to each message which it handles. Like basically unique number assigned to each message. It always goes from 0 to 10, and you always append it at the end. Like you keep appending it at the end. And I read it from the beginning. So here we see the consumers. We will talk about what consumers do. And we see we have seen that the writing part is at the end, and the consuming part, I'm saying, start from, let's say, 0 offset, 0, 1, 2, 3. In that way, when you start a consumer, it keeps reading messages from the beginning, and you can do whatever you want with those messages. I mean, you can send it to another Kafka, or you can send it to another system. Like let's say, for example, an event happened, and you want to say that how many you want to send that event to. I gave the example of Swiggy Swiggy, right? Where I ordered an ice cream from my home, from an ice cream store. That's an event. Now that event is important from Swiggy's perspective. They need to deliver that event to the restaurant. So just to let the restaurant know that this event has happened and you need to fulfill the order. Right. On the other hand, let's say they need to give the real-time dashboard to the executives to match it up to a delivery. Like let's say now there is a delivery service which is dependent on this message. As soon as an order comes in, they might have a system which is figuring out who to schedule for the delivery of it, right? And they need that data to be forwarded to the delivery service as well, so that they can figure out something. I'm saying you can reuse this event reuse this event for number of other alternatives, like sending it to other systems, using it for executive reporting, or using it for saving it in database, maybe for persistence, and anything you want to do with it. And we just saw we read and write messages to topics, and each topic has partitions and offsets. So basically, we have covered all these things that we just spoke about here: producers, consumers, topics, offsets, and all. And we see Kafka is being used heavily for streaming data. I mean, we see streaming data everywhere in the industry today, and below the few, we'll see the applications and use cases of event streaming and how that's being used today. And let's just quickly go over the companies here. We have Airbnb, Netflix, the New York Times, LinkedIn, Microsoft, all these companies which are using the Kafka today.
I have a doubt.
So here, let's go.
Can I ask you a question?
Yeah,
I'm sorry for interrupting. Yeah. You said that this message or record doesn't get deleted. Am I correct?
Your voice is not clear. It's breaking a lot.
Yeah.
There is a lot of disturbance in the voice.
You said that the message or the record doesn't get deleted. Am I correct?
No, it's still not clear. There's a lot of disturbance. Maybe we can cover that at the end if the voice is not clear.
Yeah, it's okay.
We'll cover that at the end. Yeah, thank you. Sure. So here, let's just quickly see the overview and the architecture of how the Kafka works. On the right side, if you see, I have a group of producers, 1, 2, 3, and a group of consumers on the right side. I see 3 consumers, and we have the Kafka cluster, which was referring to as a server, right? We have 3 brokers. Like each node is a broker here, broker 1, 2, 3, and that's how they work. Producer pushes the message to the Kafka cluster, and Kafka is stateless. All that state is managed by the zookeeper, like basically where the message is coming from, where the message is going, who is reading it, and which partition is it getting saved in, what is the offset to it, like all that data, all that state is being maintained by zookeeper. And which consumer has read what number of messages and what number of offsets, all that data is being kept by the zookeeper. So that's how the Kafka works in a nutshell. Now let's just quickly go over the use cases for it. We see streaming data is the practice of capturing data in real time from any source, like it will be databases, sensors, mobile devices, cloud services, anything. I mean, any device that can generate the data, you can just keep listening to the data and do whatever you want with it. And here are a few use cases for it. Like we use it for processing payments and financial transactions in real time, maybe in stock exchanges, banks, or anywhere else, or track and monitor cars, fleets, let's say some sensors, to continuously capture and analyze sensor data from IoT devices or other equipments, such as in factories and wind parks, maybe. Because let's say, we'll go through the examples as well here. So let's say when you talk about sensor data, right? Let's think about an oil field or a thermal or a power plant, for example, right? Solar power plant. We want to know, like, when something gets overheated. Let's say there is a device that is getting overheated. Each device, let's say we have 3 devices, and each device has a sensor, and it's sending the data continuously to Kafka. And on our end, on the consumer end, we are writing some logic to read the data and run some machine learning algorithm on it, or some basically, let's say, if else conditions, right? Let's say the temperature of the device is more than 35 or more than 50. There is an alarm saying hazardous, right? For example, and these things can help you avoid the tragedies. Like the recent tragedy that we had in the Telangana power plant. I think that those kind of things would be really avoidable if we have these things in place. So let's say if we have the real-time monitoring on those sensor data, we can take preventive measures and handle it accordingly. Now, let's say the moment the device sends that, the temperature for that device is, let's say, 50.5, and you have in the logic in machine learning algorithm or basic if-else condition, so just check, hey, if the event has the temperature from a device coming in more than 50, just raise an alarm. I mean, you can quickly go over and fix it so that it doesn't cause problem for the whole factory or for the whole plant or whatever. Does that make sense? Yeah, I think these are in the manufacturing industries and in the factories where we are moving more towards automation. These kind of technologies play a huge role where we need to keep track of the system health checks, safety measures, and I mean a lot more things that just doesn't come to my mind right now. So here we are collecting and immediately reacting to customer interactions and orders, such as we just gave the example of an online order through some delivery service. And the other use case that we have huge potential in is in the hospital care, where let's say the patient is on ventilator and you just have some automation and some algorithm running on it to monitor the patient health where we have lack of maybe healthcare facilities or lack of the healthcare professionals. We'll just we can just use that. It's a good, it could be a good use case as well. It's being used actually. And here we have to connect, store, and make available data produced by different divisions of the company. Like as I just said, there could be an ordering system, and there could be delivery service which is independent of independent in itself, and there could be finance which need to process that payment, and there could be reporting which needs to monitor executive reports, or maybe there is a fraud team which is looking over all these transactions and checking if this is a fraud or not. I mean, there could be a lot of use cases that we might need this data for. Let me quickly wrap up with the distributed applications here. I mean, the context of our conversation all this while was in and around distributed applications. We're just talking about how the distributed applications work, how they communicate, talk to each other, how we can, how it helps really to make a reliable system. So here, a distributed system is a system whose components are talking to each other and maybe situated or connected locally or in a network computers, as I say, maybe in different network zones or different data centers altogether, and still talk to each other by message passing. And these components interact with each other to achieve a common goal. Here, distributed app is a piece of software, I mean, as we just spoke, which is running on a distributed or cloud network. And here you can, whenever I'm saying distributed network, it could be on-premise, like on your physical hardware, or in the cloud as well, maybe AWS or Azure or any other cloud platform. And Akka is compatible. Akka offers the integration with any cloud service. I mean, it's actually it works much better and much faster with the clustering. There's a concept called Kubernetes. I mean, I'm not going to cover all those things here, but with Dockers and Kubernetes, it works perfectly fine in the cloud environments. And here we'll see the way, if you see in the diagram here, I have microservice 1, 2, 3, 3 microservices working. I mean, these 3 microservices working together as a cluster. And let's say, we'll see that example I have quickly. I'll walk up in a few minutes here. So what the advantage we're getting in here is by distributing the messaging, the processing power and storage space across these many devices, these apps are decentralized. Like, I mean, when one app goes down, when the microservice one goes down, the load will be distributed between microservice 2 and 3 that are still alive. And meanwhile, we can write some alert saying if service goes down, just let us know. We can just go ahead and start new services or fix that issue and start it up and handle it accordingly, basically. But the downtime can be reduced to, I mean, as much as possible. Basically, the uptime could be 99% if it just managed efficiently, and it can work without any downtime at all, because you have wonderful failover strategies. You have wonderful scenarios to handle how these things should work in terms of in case of failure, in cases of load. And these microservices give you don't have a single point of failure because it's just not dependent on a single service. You always have multiple services running in to handle that functionality and not have an impact on the business. Here are some of the benefits we have with distributed systems, as I think I already covered it. Scalability, fault tolerance, and low latency. When I say scalability, as I gave you the example of a university website which just handles the results. I mean, that really and the best example that we can all correlate when you're trying to, when all of us jump onto some website, it just gets very slow. So this could be a very perfect example. You can spin up few new instances and it just takes care of the traffic and doesn't impact the business. And it's when something goes wrong in a microservice, you have actors to self heal and self start themselves, and if that system crashes, and you always have a way to go and start it, and meanwhile the other services will cover up for you when you're not there, and the latency is low. Basically, the response times that you have are much faster, as it's asynchronous and non-blocking, and utilizes all your processing power and the resources that you have. Yeah, let's quickly go over what opportunities we have in Scala here. I'm just going to quickly walk you guys through whatever just Googling up here. So here you see we have lots of jobs available, especially in this field, Scala, Akka, and Kafka. If you see, I just did a search on Google saying opportunities for Scala in India. You see lots of jobs here. We have in Delhi, Bangalore, Hyderabad, in Mumbai, everywhere. If you see, the requirement is just for functional programmers having some Scala experience. I mean, you search on any platform, we have lots of opportunities for Scala as well as Akka. If you see, the requirement is specifically for Akka frameworks, 2 to 4 in Hyderabad, right? And in other, I just cannot tell you the number of opportunities exactly, but I know for sure there are lots of jobs and people are looking for developers who have an understanding of distributed systems, who understanding of how functional programming work, how all these technologies fit in together, and how these things are gonna help you in future. Let's try to search these technologies if you can online and see how we can utilize this. And here I have a LinkedIn job search. It gives us the number exactly precise. See, in India right now we have almost 2,500 jobs. I'm saying some are this in some way or the other related to Scala. Maybe Scala Java, Scala Akka, Scala Kafka, maybe in Scala as in Spark. In many other ways. We have lots of opportunities. Though we say that the jobs are not many. Even during the time of this pandemic, you see the number of opportunities you have. It has just posted 1 week ago. It has been posted 2 days ago, 3 weeks ago. You see, right? The number of opportunities are huge, especially for those of you who are in colleges and still studying. This can really be a field or a domain that you can explore and try to see if you can utilize this. And if you see the best programming languages that we have in the future, if you see the list of 10 languages, you definitely find the Scala for the future, I'm saying. And if you see I just wanted to give you guys a reference of how the programming is driven and what could the future be, especially when you're dealing with the lots of data that's coming in real time, and you need to handle streaming data and make sure that you're utilizing all your processing power that's available to your machine. If you see, here is the mention of Scala as well. So just try to go and look at how these things work. And let me quickly walk you through an example. Like there is a website called Lightband is a company who owns Akka. Like basically they are the major contributors to Akka as it's open source. And another good thing about the whole stack that we spoke about today is all of it is open source. You have their source code. You can just go and look into their source code of what they're doing and how it's working. And you also have lots of libraries or lots of support, open source community support for all these projects here. And here is the Lightband is a company. Just go and search for Akka sample cluster Scala. Like basically here is the sample. I just downloaded it and ran it for you. Maybe it just won't take you more than half an hour to test it. Here we're just trying to see how an Akka cluster works and how it is. Just try to download the example from here and try to run it as you have the instructions. We'll quickly try to go through all these. You see here I'm already running an application. So let me just stop it here and see if you guys can see here. I'm just starting this application. So these microservices in Akka run on a host and a port. So for now I'm using localhost. So each of the instance can run on a different port. You see the port number I'm giving is 25251. So I'm starting the microservice 1 on basically I don't have multiple laptops to showcase you, or I'm not in a cloud environment to run this on multiple instances. So I'm just using my local machine to show you how it works in a distributed system. So let's say I'm starting one instance on the node 1. Basically one box, you see the black command prompt is one node for me here. And I'm just gonna copy another command here and just run it in the second tab that I have. And they just mark the starting of a new node. We will start the third as well, so that we can go and look at all of those at once and see. So basically, we are starting 3 nodes here, and we'll be seeing how each of those work. If you see, this node tells us, you see here there is an event called member is up. So we will see what does that mean. Whenever a node joins the cluster and is ready for handling the traffic, it says member is up. Like member means any node joins in. This is called cluster listener. Whenever an event happens in a cluster, let's say I was telling you about scaling up, right? Where I was talking about when the load is a lot, you can just spin up new instances and that just takes care of it. So in that case, whenever a new node joins the cluster, you'll get an event called member is up, and you'll mark that member running on a particular node as up, and that member will start listening and communicating in the cluster. You see here, these nodes are still trying to join, and we'll see how that works in here. You see now it says here, it says running node on 252. Just have a look at these logs are just getting printed here, and we'll see what each of that means. You see here now it's saying member is up on this node, and it says member is up on this node, right? So whenever a node joins in, it just sends a message to all of the available nodes in the cluster. Let's say now we always have a seed node which joins, which is the first application which will be started in the cluster. And now any other application that's joining the cluster will notify the seed node that, hey, I'm here and joining the cluster. I'm here to join the cluster. Seed node will accept it, and they both form a cluster now. And when the third node joins it, the same thing happens. They just tell the seed node that, hey, there is another node who is joining the cluster, and based on the configurations, it just accepts that. And now you have three nodes in the cluster, and they all three share the traffic. If you see here, if you see, we got a message, welcome message from 25251, because this is the seed node. You see, this we welcome this node saying we accepted you in the cluster, and now you are part of the cluster. The same way we receive a welcome message here as well. We should actually. We might, you see here, right? We see a welcome message here as well from 25251. So we know these both nodes joined, and now member is up. So now this node is being told that this node is up because this is 8196 is the port for this node which is running on. You know what I'm saying, right? Does that make sense to you guys? This will mark the end of our discussion. So let me know if you guys have any questions for me. We can talk about it and discuss here. We already 13 past 12.
Sir, I got a question for you, sir. Can
Sure.
you? Okay, sir. I just want to ask, like, you were talking about Kafka, like, so, like, what Kafka version have you used for there, like? Any version you just like 2.12 or something like, or what is it?
No, in 2.0, but why would that matter? Like, what exactly is the question?
Okay, my question is like for example, I have downloaded a Kafka version, like suppose 2.12. It's 2017 version. Now I'm thinking to update the version on all the clusters on the Kafka broker. So is it recommendable so that I could update the Kafka in like that version? Is it recommended or not? Because it's a real-time environment, I want to say.
But why? What is the need? Like, I mean, we just do not upgrade the version just like that, right? But what's the need driven behind it?
Because we have been using it from 2017. Now they're just telling to update the version. So I'm asking you, is it recommendable? My question is it recommendable to update the version of all the Kafka real-time Kafka production brokers or not? Because we need to stop all the brokers, we need to stop the zookeepers. Then we need to update it. Sometimes the data can be corrupted. What is your opinion about it?
Yeah, you can plan a transition about it. I mean, to first answer your question, I'm not. I don't have a complete insight into what the latest version is because we are just using the basic. I'm just working with the basic functionalities of it. We are not using the whole capabilities that are offered by Kafka, but I do know. If you are just trying to have a transition, you can just plan a smooth transition for it. Like, let's say, for example, you can just have another node that's starting up in parallel and eventually move up everything. Like, basically start utilize whenever you're sending the new events, make sure that you send it to the new topic or basically a new node or new broker that you have. And that's how you can eventually shut down your old node.
No, they
there shouldn't be.
they are telling us to update it on the Linux server. Like, so we can't have a new node now. So they are asking us to investigate whether we can update the version on this old node. So if I see on the top couple of Apache websites like Kafka websites, because they have recommended that there could be a high CPU utilization, or they could be like data could be corrupt, or that they were telling us. So that is was my question. Like, if I create a new node, so then again I need to install it. Okay. So what about my previous
No,
slide?
when I say new node, no, when I say new node, I'm planning about a smooth transition. Like, I mean, I don't know how the system is. Like, can you afford a downtime? Like, would that be okay if you have some downtime?
Because it's you already said in your session, like Kafka is a real time streaming messages. Like, okay, so if you keep a downtime, then the users will be complaining because it's a hospital industry. Like, you got my point. So
Yes, exactly, exactly.
So,
That's why I was
yes.
telling you. It doesn't make sense to bring down the system. But what you can do is you can plan an eventual transition. When I say eventual transition, if you have one Linux node, right, you can run uh, another instance of the Kafka on the same node as well. Like, I mean, basically, well, as I just showed you the example of running an application, right, on one node, you can definitely, let's say your 9092 port, right? Let's say one of your nodes is running on 9092 port, and now you can start another node that just runs on 9093 and takes care of it. So what you can do is any new data that you're publishing from your producer, you can start publishing to that new node, and eventually everyone else on the consumer side, they can subscribe to both the events. Like, I mean, you have you have the ability to read from multiple brokers, right? You can read from like any number of brokers you want. So you can keep reading from the old brokers as well as the new brokers as well. I mean, that's what I would recommend. If the system is, I mean, definitely the systems are real time and we cannot afford a complete transition. But I don't really see the need to move because nothing
Okay.
really changed from the capability perspective.
So
Yeah,
like
that's
version up,
different.
like for example, they are updating the version. So what, like, why are they updating the version? What is the use of it?
Maybe the security patches is the primary issue that we have.
Okay.
Security updates, the feature updates. I mean, there's a lot of things that Kafka community has come up with, especially on the streaming side, on on the stream processing side, where they have new connectors and all.
Okay.
So, but most of the people do not use all the functionalities, like the majority of the people are working with just producer and consumer APIs, and they just don't what do you say, use the capability of having the streams API or the connect API. They just don't use it. So
Okay.
if you're using it, then it makes sense.
Okay, one more thing. Kafka is an open source.
Yes, it is.
So on the production side, is it open source or this paid version?
So it's everything is open source, right? I mean, why would that be paid?
Because security issues will come now, sir. Like if it's an open source.
No, I mean, there is no security. I mean, lots of the applications are open source, right? Why would there be a security concern? Like,
So-
I mean, unless you're exposing your
So
server details to someone and...
Okay, so Kafka is an open source, Zookeeper is an open source. Is it right, sir?
Yeah, the whole stack is open source. Like, I mean, the whole stack that we are talking about, like Kafka, Zookeeper, or any other technology
So Akka is also
that
an
we
open
have spoke
source.
about. Yes, yes.
Okay.
Sure. Thanks. Anybody else? Anyone has any questions? I mean, it could be anything. We can just talk.
Is it like this? We can do one thing, like we can take the snapshot and we can try working on it. Is it like that? Because we don't want to corrupt the data, we can take the snapshot of the things and.
Yeah, definitely. Snapshots are always a way. Yeah, snapshots are always a way to work with. Definitely, you can try. I mean, that's what I was gonna recommend. You can have a small POC, like proof of concept, and try because it depends on the version to version. You can try a small proof of concept to work with the version that you are migrating from and the version you're migrating to, and see how does that data work. And if you have any issues, then probably implement that on a scale.
Okay.
That would be a safe approach.
Okay. Okay. One more thing. You were showing about Akka. Akka, I was seeing it. So where are you writing the code? Like in Scala or you're writing in IntelliJ?
We can write in IntelliJ. Scala is just, I mean, Akka is a framework. Scala is a programming language we're using to write it. And you definitely use IntelliJ as the IDE for it. Anybody else have any questions?
So you were opening some 3 terminals in Akka. What is that you were showing up to?
So I was you can see 3 terminals has 3 nodes. Like I'm basically running them and running the same application on 3 different ports, right? So now my capability, whatever capability that I had, will be into 3, right? Like that's like a distributed system. And now those 3 nodes form a cluster and talk to each other to get things done.
So
that's just an example of how this.
Okay. So what do you get at the end? Like, what is that you use like Akka?
It's a framework. It's a library that gives us the capability to create distributed applications.
Okay.
As I say, distributed applications in the sense you can basically write your code. Let's say any microservice that you have, right? Like basically, if your microservice has the capability to serve, let's say maybe 100 requests per second, then if you have that application as distributed, and when you have the demands of load and scalability, availability, let's say all of a sudden your number of users has grown from 100 to 1,000. In that case, I mean, it just gives you a handy, I mean, it will be scalable and fault tolerant. Just for those scenarios, we have all these frameworks that we use it.
Somebody was asking about data deletion. I would say that Kafka data deletion there was a question probably. So there's a retention time period for it, like 7 days or 14 days. After that, you can delete it. Somebody was asking earlier like that question. But the voice was a bit breaking up, so you can answer that question if he's asking.
Oh, I see. Python is an emulator type language. I don't see. Can you read that question? I don't. There are lots of questions. So
there was a question earlier. There was a question earlier, there was a guy who was asking earlier, what is the logs should be deleted or not in Kafka? He was asking about it. So, what is your point of view on that Kafka thing?
No, there is no option to delete messages from Kafka, right? I mean, it just write to it, and the messages will get deleted automatically when the time expires, like when the TTL, when the time that you have for persistence set, when it expires, it automatically gets flushed out.
Okay. What about Zookeeper?
There is no delete on it. Yeah.
What about Zookeeper, sir?
What do you mean? Can you ask that question specifically if you have?
Because Zookeeper out.logs is storing up the files. So what is that? It's going to be deleted automatically, or you need to delete it?
No, it will get deleted automatically as well, right? I mean, basically, it's just maintaining the state of it. I mean, once the data is gone, I think the state will go as well. I mean, I need to look into that as well. I'm not sure of it, to be honest. I think we can explore that if needed.
Yeah, I've seen it. Yeah. You need to do it manually, because or else you need to write a cron job for it. So basically,
okay, I see. I'm not aware of it. That's why I said.
That's fine, sir. Thank you.
Sir, I have a question. In the company, I am working as a Kafka admin as a developer.
Okay.
So it is for admin or a developer Kafka for that?
I mean, it can be both, right? If you are working on the infrastructure side and you just want to have the role of admin, basically you'll work with. Is that what you're asking?
If suppose I have learned a Kafka, so I'm okay. Going to company as a admin and or a Kafka developer.
You can work. I mean, see, there is. It's not like you just. Yeah.
I'll take the question, Naseer. I'll just tell him. For the Kafka admin and developer, they are all developer side. You need to have programming skills, good like Scala or Java. But
okay.
Kafka admin, you need to have a good background on Linux script type. So Kafka admin is like what sir has told you in the today's lecture.
So what's the roles and responsibilities for Kafka admin?
So you need to handle the Linux proper. Is it communication is going on with the brokers or Zookeeper out? If the logs are filling up, you need to delete the logs. Is Java running or not on all the Linux brokers? This all the Kafka admin . So it's a good opportunity in that. It's everything is there in that. You can Google it out.
Yeah. Just I wrote seen on Naukri.com. There are many opportunity for Kafka admin.
Yeah,
So
we are good at like all the you need to see it like if something is logged, if in the real time I've seen the zookeeper is down, so how to recover it. If Kafka broker is down, how to get back to it. Normal state is a real environment, so you need to handle this all things. So this all.
yeah.
Yes.
Okay, thank you.
No problem.
And what is the Kafka function in means what is the partition and what is the offset?
You go on the Kafka Apache website, you can see all the definition written there. You can just can read through that all the document. You'll get an idea about it. But just type Kafka Apache, you'll get all the documentation. So you can read it and you can understand. You'll get a better understanding. Because time period, you can't discuss everything on it.
Yeah. Okay, thank you. Yeah.
Sure. Thank you, guys. Thank you for joining all. I think we can wrap up. Thank you, Habib, for answering that question. Thank you. Thank you.
Thank you, sir.
Wise for hosting the session. Thank you, Afroz.
Yeah. Thank you, everyone.
Yeah.